Hello, fellow pedestrians. Today we're talking about non-homogeneous second-order differential equations with constant coefficients again. So we have non-homogeneous second-order these with constant coefs again because we weren't done. Now, the first step we're going to take every time is to solve the homogeneous part. Uh, and we are going to denote this solution as y naught, which will be the solution of only the homogeneous part of the equation. As a second step, we're going to search for solutions of the form very likely with that of the non-homogeneous part. And we're going to denote this as yp for particular solution. The third step, the last one, is to sum up the solutions. And there you have it. This is the most general solution for, let's say, uh, we have a second order differential equation with constants a, b, y prime plus c, y is equal to a function of x. Then the solution is going to be the general solution, which consists of two linearly independent solutions plus, sorry, plus the particular solution, which represents this part, the non-homogeneous part. Now, the general rule we follow here is that when Rx, it has to do with the form of the non-homogeneous part. And we try and search solutions that are very similar to it. For example, if Rx is a polynomial, then we are searching for polynomials of the same degree. If Rx is an exponential or a linear combination of exponentials, then we search for a linear combination of the same exponentials. If it's a linear combination of sines and cosines, then we search for linear combination of sines and cosines of the same argument. If it's exponential times polynomial, then we're searching for the same types of arguments, and so on and so forth. It's pretty simple, really, and we're going to examine this through examples one by one. So let's go ahead and say we have y prime prime minus 4y is equal to e to the x. And last but not least, we'll see an example where all of what we said here is not going to work. And we'll see exactly why. Now, the characteristic equation, which solves the homogeneous part, is going to be rho squared minus 4 is 0, meaning that rho is plus minus 2. So the homogeneous solution, sorry, C naught, y naught, is e to the 2x and minus 2x, the roots of the characteristic equation. Now, we have an exponential of x, so we're going to search for a solution where a is a constant, a of e to the x, meaning that yp prime is going to be this guy, and also this is the same. We're going to take this and plug it into our original equation. So we have a e to the x minus 4 times a e to the x equals e to the x. This all cancels out, meaning that a is just minus 1/3. So finally, the solution is y naught plus y particular. So the one we wrote above to the minus 2x. So this is the solution. So minus 1/3 e to the x. Another example. Let's write it with red. Let's say we have y prime prime plus y is equal to cosine 3x. The characteristic equation is rho squared plus 1 is equal to 0, or rho is equal to plus minus I. So as before, we know that this is just the 1 sine x plus the 2 cos x. And like we said, since this is the non-homogeneous part, we're going to try and find a solution that has a constant of the same argument, 3. Now, yp prime is going to be minus 3a sine 3x, and y prime prime is going to be minus 9a cos 3x. So we will plug everything here, minus 9a cos 3x plus 9, a cos 3x is equal to cos 3x. This cancels out, so minus 1 over 8. And the final solution is this guy here. So the general solution of x plus 2 cos of x plus the particular solution. Another example. Y prime prime minus 3y prime plus 2y is equal to 2x squared minus 3. Now, the characteristic equation is rho squared minus 3 rho plus 2 is equal to 0. And rho is going to be either 1 or 2 if you solve this. Hence, the general solution is going to be e to the 2x plus constant e to the x. And like we said, you have a polynomial, and we are going to search for a solution of the same order. But you also need to include missing terms if there are any. And there is a missing x to the 1 here, meaning that we're searching in the form of ax squared plus bx plus a constant. So y prime is 2ax plus b, and y prime prime is going to be 2a. Now if you plug everything, 2a minus 6ax minus 3b plus 2ax squared plus 2bx plus 2c is equal to 2x squared minus 3. Now group every term together. We have this is the only x squared, so x squared times 2a plus x, where we have minus 6a and plus 2b, and 2a minus 3b plus 2c equal to 2x squared minus 3, meaning that this is equal to this, so a is 1, right? And also minus, this is 1, so minus 6 plus 2b is equal to 0 because there is no x term, meaning that b is 3. And finally, putting everything here, we get that this is 2 minus 9 plus 2c is equal to minus 3. So c is just 2. So finally, the solution, the particular solution, is x squared, because this is 1, plus bx, so 3x, plus c, and 2x e to the x plus this. Let's do another one. Y prime prime plus 6y prime plus 5y is equal to 2 cosine of x plus 6x squared. Now, the characteristic equation again is r squared, rho squared minus 6 rho plus 5 is equal to 0. And rho is going to be either 1 or 5. So the general solution is going to be c1 e to the 5x from here and c2 e to the x. Now, the particular solution is going to be a cos x plus b sin x plus ax squared plus bx plus c. Why? Because we said that when we have a linear combination of many terms, we are going to search for the linear combination of these terms. So we're going to search for something like this. Now, I'm not going to do the calculation of all of this, but if you do it and plug it in the initial differential equation, what you will get as a solution is 1 over 13 of 2 cosine of x minus 3 sine of x plus 6 over 5x squared plus 72 over 25 of x plus 372 over 125. Kind of pesky, but okay, had some calculation, but it's not that difficult really. And of course, the final solution is this guy, so why not plus yv, and you're done with it. Now, another example. Y prime prime plus y is equal to 2x e to the x. Again, the characteristic equation is rho squared plus 1 is equal to 0. So this is very known, plus 2 cos of x. And we'll search for a solution of this kind, so ax plus b times e to the x. Now, y prime is going to be um, a e to the x plus ax plus b e to the x, and y prime prime p is going to be 2a e to the x plus ax plus b e to the x, and plug everything in. 2a e to the x plus ax e to the x plus b to the x plus ax e to the x plus b e to the x is 2x e to the x, and finally 2ax e to the x plus 2 e to the x a plus b is equal to 2x e to the x, meaning that a is equal to 1 and b is equal to minus 1. So finally, so 1 sine of x plus 2 cos of x plus, which was it? It was this guy here. So this 1 is minus 1, so x minus 1 e to the x. And now, let's take one last example. There is a reason for this. This is an example where everything we said is going to fail. And we'll see exactly why. Let's say you have a seemingly very easy differential. If this was a plus sign, it would be very easy indeed. So minus y is equal to e to the x. Try and solve it when this is plus. Now, this is just rho squared minus 1 is 0, in that rho is plus minus 1, right? So the solution, the general solution is the 1 e to the x plus the 2 into the minus x. Now, you can already starting to see the problem. If you really uh, pay close attention to the solution, to the general solution, then you will find the solution we were going to search for would be something like this, right? Because this is the non-homogeneous part. But this is already in the general solution. So searching for a solution of the same kind is searching for a linear dependent solution. It's not going to help us at all. Now, in this case, what we are going to do is invoke our good friend, the linearly independent solution of what we were going to search. So we're going to assume a solution where what we were going to search is going to be multiplied by a function that depends on x. So a linearly dependent solution of what we were going to search again. In this case, in this type of differential equations, we say that there is a resonance of the non-homogeneous part with part of the homogeneous solution. So anyway, we're going to search for this kind of solutions. So we're going to have y prime of p going to be to the x plus u to the x, and sorry, y prime going to be prime e to the x plus 2 times to the x plus u e to the x, and plug everything in, and e to the x are going to drop, So you get finally that u prime prime plus 2u prime plus 1 is equal to 0. And this is very easily solvable if we reduce the order in this way. Of course, this is also um, second order with cost coefficients, but another way to solve this, since there is no u, there's not the function we're searching for, is by using this substitution, right? So this transforms into prime plus 2u minus 1 is equal to 0. Uh, Sorry, this is right, which is nothing more than linear first degree like we already seen. So this is e to the minus t to x is equal to constant e to the minus 2x, or is minus 2x is x integral dx over e to the minus 2x, which is going to be, this and this cancels out, e to the minus 2x over, so over 2, yes, into the 2x plus a constant, or 1 half plus a constant e to the minus 2x finally. So this is uh, the, so u is x over 2 plus the integral of this, another constant e to the minus 2x again, don't really care, plus a constant, another constant. So finally, the particular solution is e to the x times chi. So the general solution is this to the x plus 2 e to the minus x plus the particular solution. So plus e to the x uh, x over 2 plus a constant e to the minus x plus another constant e to the x. And you see this and this are going to collapse. This is the same. And also this is the same. So this is the final solution, because the other terms were just linearly dependent on this and this, right? So that's pretty much it for the non-homogeneous differential equations with constant coefficients. On the next lecture, we are going to check more complex differential equations where the presence of x is there, so we don't only have constant coefficients to deal with. And we'll see how we can tackle this problem by using, when it's possible, symmetries, and how we can reduce differential equations of second order to first order when possible. So that's pretty much it. Thank you all, and I'll see you on the next video.